Hey everyone, and thank you for joining the AstrumDrive podcast. My name is Ivalu Vasilev, and this morning we're joined by Nelson. Nelson is the head of our physics department. So during the today's session, we're going to do several things. We're going to review what we did in the last sprint. We're going to go through the current sprint planning, and also we're going to do a short overview about the tasks we're currently doing. So having said that, Nelson, let's go ahead and give us some idea about the sprint 3. What exactly did we do during this sprint?
Thank you, Vilo. Hello, everyone. Yes, this was a very interesting sprint. We started now I think the first steps into the best part, the most enjoyable part of the research, I believe. And let me try to lead you step by step because this is a sprint that is a bit long, but quite interesting. And I think from this point on, it's important to keep a really strong order of how the things are exposed. So first, we're continuing with what they did with the last sprint. We were studying the Natarius metric the deeply as we can, and also we are studying how to implement other conditions for the energy momentum tensors and how they appear in different contexts uh, in reference to other works that I will tell you about very quickly. So first, what we find out, this is just reviewing Natalia's article, this first ticket I can talk about is that we showed that what Natalia did, basically that is not compatible uh, positive energy configurations that you can use with Natalius metric, and at least in this form, in the form that is exposed and published by Natalius in his first approach. This was kind of easy to see. Uh, just requires to understand a bit about the ADM formulations of general relativity that I think I talked about before. But if you have any other questions about it, please put it down in the box. So then one of the things that we find out is that yes, this space-time just violate some of the energy conditions. We have basically four energy conditions. They are more or less a way of saying that you cannot violate some specific law for natures. Like there are the different ways of saying you cannot move uh, in a local frame faster than the speed of light, and you can have negative energy. This stuff are related in some way, and these are energy conditions that are you call dominant energy conditions, strong energy conditions, weak energy conditions, and the null energy conditions. Not all of them are proof that have to be uh, satisfied in order to have a physical situation. In fact, there are some situations that have I learned recently, you can violate some of them. But basically, what is believed is that in quantum field theory, for example, you're not able to violate the null energy conditions. Apparently, this is the one that has to be satisfied for every system. So in that scenario, we check out that uh, in case of Natario, we are violating the strong energy conditions, and we check using also the Gauss-Codazzi relations that these observers that we have, the Eulerian observers, which are the free-fall observers, uh, this is of course in contradiction with this with, with, with basically with the strong energy conditions. We didn't check the other ones yet, but we jump into some other work in that direction. If you follow Natario, you see that because it's a bit more general, it includes as a special case the Alcubierre's metric. So we went to Alcubierre's metric to review some of the work. This is the work of last year works, Santos Pereira team, that is called Perfect Fluid Warp Drive Solutions with Cosmological Constant. It's very nice because basically they took Alcubierre's metric and they started to they apply field equations. You calculate everything you have, and you calculate the field equations, which is Einstein's equations, with some perfect fluid configuration as the energy momentum tensor, and also adding cosmological constant, which makes a big change in the thing. So they consider several cases, and we were working on this, and we find what they found in some way. Basically, you find the same Einstein's equations, and then you try to figure out how to solve these equations. Not really solve them, but to figure out how to rewrite this in a way that is clearer to can interpret it before even solving the equations, the differential equations that appears. So what we found is that uh, with this in mind, we found that, of course, the cosmological constant adds a new term, which is important because in addition to the energy momentum tensor, which also gives you uh, we have now a cosmological constant that can be positive or negative. So this is interesting because this is the way that you can have something extra. It's quite simple indeed, but it's more or less the simplest way you can put something extra. It's like a background thing that is in the space-time. Anyway, working on these equations, which is I believe that the first steps very interesting here is the constraints that you can find using Einstein's equations, which is basically saying that if you observe the set of equations that you have, you basically combination of these equations, you got the certain constraints that are applied on the derivative that appears there. So basically, let me put it in the most simple way. In the Alcubierre's metric, we have a function that is basically shapes the way of the bubble, and this shapes we can call it beta, and this beta functions appears in the Einstein's equations as a derivatives with respect to some of the coordinates. And what we found is that there is a new unique way that if you combine Einstein's equations, it's going to give you that some of the derivatives are always zero, which is strange because we found that some cases that were studied in these papers, they consider this as possible, as they can be finite, I mean different from zero, and it's not possible that they are. If you take this to account and you find that this, which is the chief factor, you find that these derivatives are always zero, there are a lot of changes in the cases that you find in this review. For instance, you find that apparently this is something that is a preliminary result, that the weak, the null, and the dominant energy conditions are satisfied, which is something new. These are always satisfied. It's not a matter of that you can say, oh no, we have some energy momentum configuration that is helping us. No, these are always satisfied just by putting these conditions and with the perfect fluid and cosmological constant. But even without the cosmological constant, these are satisfied. This is something, of course, we have to check because it's in contrast with other articles that we review. But anyway, this is an interesting result because we're certain that what we found, the conditions, the constraints, what we found with Einstein's equations are okay. The only case that is apparently not sure is the strong energy condition. Apparently, it's not satisfied as we would expect it because this is the result that is found by Nantarius. And basically, we have that we have the energy conditions. These strong energy conditions tells you that some Einstein's equations are equals to minus the density energy. So okay, that's the known result that we were expecting. But one thing also appears that we think is interesting, that from Einstein's equations, the same derivation we did before for the constraints on the derivatives of the beta functions, the chief vector, you also find some state, a specific equation for state. And this specific equation state relates the density energy and the pressure that appears in the perfect fluid and the energy momentum tensor. So if you, it means that you can just basically change into this strong energy condition the binus density energy for pressure. These are, in fact, it's a linear dependence. So, and that at the point means that you have something that is dependent of the pressure and is positive pressure, probably. And that gives you an idea that, okay, pressure now plays an important part in here. I mean, from this approach, you see the pressure can play a very important role that we have to examine it later. But this is an interesting, very interesting result that we found. Probably the most interesting one. Of course, we're rechecking everything, but it looks very good. We check all these calculations by hand. We did it also with Mathematica, as we also always do, and it looks okay in every aspect. And finally, but basically what we finished the sprint with uh, understanding the last part of Natarius' work, because one thing we're aiming for is to rewrite the warp drive in a spherical way. Has been done by many people, but we are figuring out a tiny bit different way of rewriting the warp drives in spherical coordinates, and we review the way Natario does in his article. But what he really do in his article is rewriting the shift vector in mapping this into a symmetry spherical way, which is good because this is something that we can use. And then this, we're going to use it later when a spherical warp that we are thinking. This is still in progress, this thinking. But basically, that's what we end up with, that finding how to calculate the strength tensor in this case. The strength tensor is now related with the the string curvature, which is also very nice that you can find these tools that comes from fluid dynamics, like the strength tensor, that have this very perfectly manifestation, let's call it that way, in this ADN formulation for general relativity. It's very nice. It's very nice to find this kind of things that maps perfectly. So it also can give us some idea that we can talk about some fluid analogy that people have worked before with space times. And basically, that's it. That's what I've done during the spring.
Nelson, it was indeed very exciting sprint. So Nelson, can you please tell us a little bit more about the new warp drive metric we found and what are our plans with this metric? What kind of tests we're going to run on the top of that?
Okay, sure. Well, the metric that we are thinking about this is we're proposing is just let's say in this way. Uh, Basically, we are trying to keep the basic components that defines a warp, in using a bit of what we read in some articles like Notarios, but also some other articles, new articles. Lens article is very good. The public article is also very good. Last year's articles, and they define more or less different ways. They talk about what's the physics of the warp drive, and the physics comes in when you talk about which is the direction that you say this direction is going to be the direction that the chip is moving. So we were thinking uh, about the intuition of motion in there, and instead of breaking the spherical symmetry that you have by saying we're moving in the x direction, for example, we're thinking more in what happens if the intuition is correct if you have a motion just saying in the radial direction, which is could be any radial direction. And then we were thinking about what are the implications of this in terms of the motion, if it's going to give us really a warp situation, And apparently, yes. And this changes a bit how the metric is written, and also probably we have to calculate. We change also the way you can put in energy momentum tensors that has more freedom in the sense of can get anisotropies, for instance. Also, it's probably going to make easier to define different observers because it's a spherical symmetry. We know how things work with spherical symmetry. So we're basically trying to push a bit more in that direction so we can use the tools that you already know. And that's the basic idea. Let's call it that way.
Excellent. Thank you very much, Nelson. I mean, it was a really exciting sprint, so we're going to continue to work on this work metric during the next one. So, Nelson, let's go briefly all over the sprint planning we did for our current sprint, sprint 4. So let me just go to the appropriate screen and please tell us a little bit more what exactly our goal is for this sprint.
Sure. This in this during this sprint we're working. Well, we already finished Nantarius paper. We have to still work a bit more about the problem of the horizon problem, which is a problem that we might face a bit in the future. But at this point, we're working on that. We're revisiting basically a couple of articles that are, I think were important. Basically, an article from Lens is like a last year article, which is very interesting because he makes a change in how which the type of observer that you put as an observer in the calculations of the Einstein's equations. Usually, as notarios do, you use Eulerian observers. These Eulerian observers are free fall observers. These observers that follow the geodesics that the space-time is telling you how to move. And this observer is a bit more complicated. It's a functional dependent observer, and it's quite nice because it gives you like different results than more complicated but different results, and you can add it allows you to have positive energy configurations. So it's quite nice, and we're going into that direction because we want to see what happens with different observers. There's going to be there has been a bit of controversy related to this because you have to prove that all these observers are uh, obey some of the energy conditions. And apparently, and this is something that we also were looking for to see, understand, is like if this is just a set of observers that is satisfying these energy conditions. In this case, is the weak energy conditions, and see if this is just a set and not the whole observers, and just a subset of this. And also, if this is so important in terms of how you interpret the warp drives. And this was an article. I think this is this year article that is also uh, goes in this direction. But basically, we're looking to see how these positive energy solutions appears when you change the observer, which is basically changing the shift vector that appears in the warp drive. Also, we are going to check, uh, uh, how to address these solutions we were thinking about uh, in the spherical symmetry warps, and consider different dynamics of solutions, different sources basically, and see if we can get, for instance, the same classification that Santos Pereira tried in their article, but in the in the way we did find it for our metric proposal, the one we have, and if see basically two things: which are the constraints we have of the elements that appears in the metric, and the other thing is if we have some liberty or not about the equations for state that appears there, and how much we can play with this energy momentum tensor, maybe adding or not, if it's possible or not, add more ingredients, which is what we are aiming for more complexity in the system. Basically, that's the idea of this sprint. It's a very interesting sprint. We're working very hard for that.
Very much, Nelson. I think it's quite interesting. So according to this, but it can have local solutions with negative energies. Is this correct?
Yeah. Okay. Let's see. What we have is energy conditions are a different way for constraining the physical things that we know. So locally, it's not possible to have uh, faster than light motion. It's something that you don't want that because it's basically violating special relativity, and we know that it's not possible. It's been tested a lot, and this is based on foundations of special relativity. But so locally, you cannot have that. What happens globally is a bit more complicated. Globally, it appears that well, once you're looking at the global, you have to define what is global. And global in the sense that it's global really for the whole space-time in the whole universe, and it's not. So the whole space-time is different. So you see, it's quite complicated to say what if it's something that we are trying to understand better because there are a lot of different opinions. You have local in the sense that a local observer that has a flat space-time sees something that is not moving faster than light. You have then a bit less local, let's call it that way, that appears that is a different space-time, and you allow some uh, other kinematics that allows you to have a displacement that looks for another observer that is also not global because none of these are completely global. There's no way of global observers in this sense because the space-time is not complete. So, but you have another observer that is a site that you can look at this different, and this observer has probably also maybe flat space-time because it's very looking at this very far from the object, the chip, for instance, that is moving. So this different type of things is you're looking for. So we're looking for a combination of this observer that is going to give us a physical situation with the outcome that we want, which is having some displacement that appears to be faster than light for some observers, but for other is not possible. And in this playing is that where you find that some of them will see negative energy and some of them don't see negative energy. And this is what is not well understood. Well, I said it's not well understood. A lot of people work on this seems to understand very well this, and I agree, but it's under very specific situations and very specific constraints. So basically, we're pushing those constraints forward. That's what we're trying.
So, Nelson, this is quite interesting discussion. Um, but I think that maybe we can stop for now because we don't want to make this session too long. But is there anything else you want to say before we close for today?
Well, no, just please ask any questions. Really, we're getting into the very exciting part of the research.
Very much so, very much so. And Nelson, okay, well, thank you very much for your time today. And if you guys listening this podcast enjoy it, please like it, share it, and if you want to support us, please become our Patreon. And having said that, let me wish all of you to have a very nice and successful day.